Alright people, welcome back. So in today's episode we're dealing with a medium problem. This is again under the dynamic programming section, and it's the first time we deal with a medium problem under this section. So let's see what this problem has as challenge. You are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Okay guys, this feels very similar to the problem we addressed last time, which was trying to calculate the minimum cost. And now instead, we are trying to calculate the maximum gain earning that we can get. So let's have a look at the examples. So for example, here nums is equal to 1, 2, 3, 1, the output is 4, and that's straightforward because the best to rob are at index 0 and 2. 1 plus 3 is equal to 4. Here instead the output is 12, and this is 2 plus 9 plus 1. We're losing the 7, the 7 as an amount of money we can get, but of course this is adjacent to 9. So either we take 7 or 9, then we decide for 9, and we take the other 2. Also 7 plus 3 is not the equivalent to 2 plus 9 plus 1. Okay, so now we want to solve this problem, and I see a few things that we should take into account. First, not always the best solution is to rob as many houses as possible. For example, here, the length is 5. But what if here we had 100 and 1000 at index 1 and index 3? Then the best solution would have been to rob those two houses. However, it feels like, let's see that here we have 1000. Then still it's a good idea to rob another house, because even though the ratio is very low, it feels to me that the best length is going to be always, like if nums has a length, let's say that n is the length of nums, then if n is even, then of course, no, it's not so easy, because of course, like look at this potential array, let's say 1, 1000, and then this is actually, let's call it 100 to make it easy, and then 1, 1, 100, 1, 1, 100, 1, yes, this way. So here the best solution is 100, 100, 100. And the length of the array is actually 9, isn't it? It is 9. So it is possible that in an array, the best solution is not even the half of the length of the array in terms of the numbers of houses we rob. It can be less than that. It can't be more than that. So let's say that we are around a bound between 1/2 and 1/3. This is what we can do. Actually, in case of an odd number, it's we can also have more than 1/2 of the total length of the houses to rob. But you saw my reasoning behind this. So if we use the same approach we use with the stairs, it feels like we're asking, okay, let's see that we have all these houses. Now, let's see if we ask ourselves something like, what's the gain that I get if I rob the first house? Is gonna be 1, right? What's the gain that I get in case I can rob in the first 2 houses? It's 100. What's the gain I can get in case I have to rob in the first 3 houses? Well, the maximum gain I can get here. Yeah, I think the approach we can use is the same as the one before. So for each not amount of houses, but for each index of our array, I calculate the best, the maximum gain I can get, provided that I want to end up in getting the robbing the house at that index. I don't know if this works. We can try though. So I can say something like, I can write down an array gain, and then I can just say that. Okay, let's ignore for a moment the possibility that n can be lower than 2. And then okay, so I think the reasoning works. So we just say for I in range, and then we have to start at 2 to n, maybe n plus 1, or maybe not actually, or maybe yes. No, maybe not. Okay. So what we do is to simply say that gain that you can get at index, let's say I, is equal to what? Certainly, it's not equal to the gain at I minus 1, because you have to actually avoid that. So this is basically equal to the maximum between all the gains until gain I minus 1. How can I write this down? Something like that. Plus nums I. And so on and so forth. And then we return max in gain. No. We return gain n. No. We return max in gain. Really, guys, I don't know what I'm doing. I really don't know what I'm doing. Okay, so here it will throw an error, but that's fair. That's fair that it throws an error, of course, because we didn't initialize gains 1 and 2, right? Okay. So the gain that I get, no, actually I can initialize gain as cost, as nums. Maybe it's better to initialize. Yeah, maybe you can do nums, like I can just copy nums and then I can re-update it. No way it works, guys. No way it works. This is crazy. Okay, let's submit it. Let's see if it works. No way, guys. No way. Really. I am super happy that it worked. I'm really surprised that it did. So this reasoning is actually correct. Okay, let's see how we can optimize this algorithm. So I don't know if I was clear about my idea about how to solve this algorithm. The idea is that we have a bunch of numbers, and then we calculate the maximum gain actually not the maximum gain. We get the maximum gain that we can get, provided that we end up in robbing. So gain is an array that contains the maximum gain we can get, provided that we end up in robbing house with index I. Okay. And how do we calculate this? It's basically the maximum of the gains we can get until house I minus 2, and then we add what we get by robbing nums I. Now, what's the idea? Why it does the work? Because of course, if we calculate all the gains that we can get, the best gains we can get, provided that we end up in all the different houses, then of course we end up with somewhere there is the maximum gain we can get. So at that point we can just return max gain, and we will return the maximum gain. However, now that I think about it, here we have like this is as complexity on. So it's okay to have here, this also max gain as a complexity of on, but it doesn't matter because we also have a complexity on here. The problem is here, we have a maximum in the for loop, and the maximum is between this gain, like this array can get to on. So in worst case, this is going to be on, and we don't like this. We don't like this because this has time complexity of O(n) squared, which I don't know if it's the best complexity we can aspire to. Okay, guys, I think we have to change strategy because it is. I'm thinking about another possibility, like another way to imagine this dynamic programming approach. Let me think a bit. Okay, so I think we can delete all of this because this is not the best solution, even though it worked, and I was very happy that it did, but we have to come up with a solution that runs with a lower time complexity. So my idea is to define the array in a slightly different way. So tell me if this is reasonable. So the idea of returning dp n minus 1 is okay. Sorry. Come on, bro. Okay. Returning the last index of our array that stores iteratively the best solution is a good idea. The point is we don't want to return the maximum gains that we can get, provided that we want to utilize the index at which we are storing the maximum gain. We just want the maximum gain at that, like, provided that we have that number of houses. How do we store this? So the idea is that we have a for loop, for example, for I in range to n. But then what we can do is to simply say that the best solution at index I is equal to the maximum, but this time it's the maximum between two elements. So the maximum between the best solution at index I minus 1 and the best solution at index I minus 2 plus nums I. Now, why does it work? Let's go delve into a few scenarios. Suppose that the best solution, the best solution possible has dp I minus 1 inside it. Okay. Then this is okay. Yeah, no, I really think it works, guys. But can it work just like this? No, of course, because here we have to add in, and because n is not defined, and what else? Because dp is not defined, of course. Of course, dp is not defined. What else? It's just wrong. Yes, but that's because we didn't initialize dp0 as nums0. Actually, we can initialize dp as the copy of nums, as we did last time. And now it's going to be correct. Yeah, that's crazy. That's really crazy. And what if I submit? It's wrong. So for nums2i, the output is 2, 1. The output is 1. But the expected output is 2. So at this point, so if n is less or equal than 2, we just return the maximum in nums. And this problem is going to be solved, I suppose. Yes, but 2, 1, 1, 2. The output is 3, but the expected is 4. Okay, let's see what happens. So for I in range to n, so I is equal to 2 now. dp of 2 is equal to the maximum between the dp of I minus 1, so 1, and dp I minus 2 plus nums I, which is 3. And that's correct, because the options are 3 or 1. Yes. So for I, now I is equal to 3. So I is equal to 3. Now what's the maximum between 3 and 1 plus 2? Oh, I see the problem. I really see the problem. The problem is dp1 is equal to 1, but this is incorrect. It must be equal to 2. So we can do something like dp0 is equal to nums0. dp1 is equal to the maximum between nums 0 and nums 1. Feels like this is the only way. And then this n is required. Do we have any constraint of n on n? Yes, so n can be only equal to 1, and so we return nums 0. Then we return, yes, we can do something like this. And then we return dp 0. Then we actually have to initialize dp, so maybe it's a good idea not to do that now. No, forget about this. Yes, something like that. Return nums 0. Then we define dp, which is equal to nums like this. Then dp1 is equal to the maximum between nums 0 and nums I. Now it should work. Let's see if it does. It does. Wow. Okay, super happy. I don't know if this is the best solution. Memory-wise, it's still on. However, complexity-wise, it feels like it is on. So in terms of time complexity, we did a good job. I think at this point, what we can do is to simply initialize as before, prev2 as nums 0. Then we can initialize prev1 as the maximum between nums 0 and nums 1. And now for I in range, for I in range 2n, I have our current value, which is equal to the maximum between prev1 and prev2 plus nums I, and then initialize prev2. I reinitialize prev2 as prev1 and prev1 as current, and then I return current. So we basically are doing the same thing, but this time we're actually storing just 3 numbers. And if it works, then the memory... No, it doesn't. What's the problem? Yes, in case we are skipping, so it's better to write down if n is equal to 2, we return... Okay, you know what? We're going to do this. We are going to define previous 2 immediately, and then we return previous 2 if the length is equal to 1. Then we define previous 1 as the second thing, and if n is equal to 2, we return previous 1. Then we do the for loop and we return current, and now it should work. Yes, let's go. It does work, guys. It does work. Okay, guys, I think this is the best solution ever because it has time complexity on, space complexity O1, and I don't know how to improve it furthermore. So this was our first medium problem. It was harder than the easy problems that we dealt with last time, but it was very nice, and I'm really having fun with these dynamic programming problems. So thank you very much, guys, for watching this video, and see you in the next episode.